Okay, thank you very much for the kind introduction. So this is about architecture diversity, and I realise that I'll probably have a grand total of about 1.5 minutes allocated to me at this stage, but I'll do my best to move along and provide some information of some of the things that we've done at the University of Melbourne. I have, of course, a set of necessary and sufficient definitions that have to be provided in such a presentation, but of course they don't actually have to be terribly detailed because most of the people in this room are well aware of them. What I find interesting on top of all these is if I'm going to talk about a container on a virtual machine on a high-performance computing, I have to provide these descriptions so people, at least there is some sense of being close to what I'm actually talking about, is where these actually came from historically. So of course from the very start of computing, things were engineered to be high-performance computers. We typically think of clusters as being a little bit more recent, but when you look at it historically, as early as the 1960s, customers themselves were creating their own clusters from the resources that they had. Likewise with virtual machines, if we're going to talk about full machine virtualization, we can find that dates back from IBM's CMS system from 1967. And likewise, hypervisors, containers, derived from the chroot command, originally from version 7 Unix in 1979. So what is new is, what is old is new again, and we find ourselves in a situation where we are adopting different ways of implementing various, I guess we'll call them architectures within single systems. So we know how awesome high-performance computing is. Everybody in this room is deeply delves into that industry, and we're very, very happy with how we can put together in the contemporary environment using basically commodity server hardware and a good high-speed interconnect. We can scale up with some operating systems that are better suited for high-performance computing than others. We try to optimize our source codes because we want to actually get the performance improvement, even if it's even if it's relatively small, it's still worthwhile. And of course, in some cases, if you can actually get extraordinarily impressive performance improvements compared to the packaged versions of software that we get. But this doesn't come without its problems. We do know that there are problems. We know that there's difficulties in ensuring some sort of ensuring software build environments, particularly, of course, when various types of software come with various extensions themselves, and those extensions themselves have their own version numbers and what have you. I can think in terms of things like Python and R, which have got their own packages or extensions, and if you try to tie those to a particular version number, then you've got another stack to look after, and that can be quite challenging. But it can't be avoided in a sense. We actually want to ensure that we have got the best environment and the most consistent environment for people. We know that consistency is extremely important because we know that you can't there's an enormous risk of going out there and producing software results which is not reproducible. No good to write your paper. You're doing a massive statistical analysis, and halfway in your paper, and you said, "Oh, and then the sysadmins changed the version of R we were using, so we used that instead." And that can even apply right down on the actual extension level as well. And one thing that we keep on finding is that there is not as much training as we should have that's available. And that's a very big deal because, of course, we are dealing in a world, as we've heard so many times over the past 2 days, where data sets are increasing And as we know, they are increasing in size faster and significantly faster than people's standard desktop environments can keep up with. So eventually we find that researchers find themselves in situations where they have to come to us and they do need that training. They don't get taught it along the way. There's a bit of an assumption that like somewhere along the way of their undergraduate degree they'll find themselves in a situation where somehow magically through osmosis they've learnt some high performance computing skills. Simply not the case. The people who turn up to our training sessions, most of them have got minimal, if any, exposure to the command line environment to begin with. However, fortunately, they are smart people, postdocs, postgrads who knew, and they tend to largely pick it up in just a few days. So HPC is great, traditional HPC is fantastic, but it does have its own issues. So this is why we did things a little bit different at the University of Melbourne with Spartan. We did have a traditional HPC system, ran from 2011 to 2016. It had what you would expect, a moderate number of users, good number of projects, but we, like most places, were facing a sort of technology refresh, and the question was asked, what are we going to do? And as usual, you would find that there was, when we do a user review, they ask the same sorts of questions or give you the same sorts of answers. They want faster processors, they want more RAM, they want a faster interconnect, and really what all those things were saying is, we don't want our jobs to sit in the queue. Likewise, there was a question on whether we needed to actually have a local HPC at all. Surely we could actually get all this moved to one of the national facilities. And there is data transfer and policy differences, issues and differences, which justified at least a smaller system in-house and perhaps acting as a transition to the peak facilities. What we did decide to do was to incorporate a great significant component of the Melbourne node of the Nectar OpenStack Research Cloud, because when we actually conducted our survey, not on the user level but actually on the job level, we found that a significant proportion of the jobs that were being run on a single node. So it didn't make sense to actually pay the money for a high-speed interconnect that wasn't actually being used. The nature of the various software applications that were being run meant that a large proportion were quite happy on the single node, and because we had a good quantity of virtual machines available, well, we could make use of that. For the smaller, what we call the bare metal partition, we used Roxy, which provided us with, at a cost-efficient level, speeds that were FDR and InfiniBand equivalent, in fact, better. So that was very good. We are able to run our login and management nodes as cloud VMs as well, which of course means that deploying a new login node is relatively easy. And in case of disaster, we should be able to get ourselves a new management node up pretty quick as well. So that is all very good. So core partitions separated into the physical partitions designed specifically for those multi-core, multi-node jobs, cloud partitions, single or multi-core but single node. And we've also got, due to the peculiarities of way that things are organised, we also have some specialist partitions for particular projects that have turned up and said, hey, we want to actually have an area reserved for us and us alone, and here's a bag of cash to sort of justify that, or here's some hardware, can you attach that to our system? So that allows us to break it up quite nicely. We use Slurm for our workload manager. We we've got a bit of a community around Slurm in Victoria. We find that the extensions and reporting and accounting tools that it offers is very useful. We use Easy Build to try to ensure consistency in not just the build but also in the tool chains. And we have an interesting configuration management system where we combine Puppet, Git and Gerrit. So if we make changes to our core configuration, that basically is made as a change in our Puppet files, which is then kept in a repository through Git, and then through Gerrit we allow for a checkup. So when a person makes a change to the core configuration, it requires another sysadmin to say, hey, actually you've actually done something that's going to be quite dangerous here. It does its own sanity checks as well. So we have a paired systems administration, and that actually works quite well. Fortunately, we're in the same room, so when you actually need something done fairly quickly, you can tap them on the shoulder and say, can you stick an eye on over this? And the other thing is extensive training program and specialist workshops. That's made a huge difference for the capacity and capability of researchers to engage with high performance computing. So after a year, our relatively small cluster really, it's only a few thousand cores, probably 4,000 all up if you include all the specialist partitions, has done over 1 million jobs, which is pretty reasonable given that scale. And the questions that we typically get asked are actually fairly sensible questions, because the people have gone through an extensive training program. They know how to submit the jobs. They know the how to do their job arrays and job dependencies, their interactive jobs, and so forth. So that's actually been useful on both a general sense and also for the specialist sense, because we can adopt the model for the particular software stacks that people are using. So, for example, about a month ago, there is the Origin Centre of Excellence, which looks after adolescent mental health. And we were able to concentrate all the software examples on their particular tools, such as FSL and FreeSurfer. So that gave them things that they were familiar with, and they were able to see how they could put those things in a HPC environment and get results faster. So small physical partition in proportion to the amount of jobs that were being submitted that were multi-node. You would obviously change these percentages according to your own environment. Much larger cloud partition. Yes, there is a small overhead by running a virtual machine, but that's not an enormous problem if you're not going multi-node. We have a faster interconnect for the physical partition, and of course, when you've tried to, you can still do multi-node jobs on the cloud partitions. In fact, we actually have seen examples of that where people have want to actually have a much higher core count, but they just have to realise that if there is a lot of communication going on between the nodes, then they'll notice a significant difference. Over 600 users, which is not bad for something that's just over a year since the official launch. We do have a small GPU partition at the moment, but we are engaging in the process of doing a very, very large increase over the coming year. And this small experimental system is about to make its way into the top 500, or to satisfy the people from BOM, at least those machines which are reported in the top 500. A deserved comment, I think. So, as mentioned, our cloud partition is virtual machines on an HPC. And this has given us a great deal of flexibility, because depending on, with the existence of the Nectar Research Cloud already been established. It has allowed us to sort of like extend or shrink the actual size of our HPC as needed. There was an initial hope that perhaps we could actually make this even bigger with the use of virtual CPUs, but of course, in the HPC environment, that's not much of a goer. Most of the processes that occur on the Nectar Research Cloud are usually computationally less intensive than what you find on an HPC. So we did an early experiment did suggest there were noisy neighbour effects and there were time mismatch errors. So we got rid of that. So we went all for a one-to-one system. One of the things which does get asked is, well, hang on, you've got virtual machines on an HPC. What does this mean about user permissions and things like this and different images? Something to clarify is that we do, in our particular environment, we have got a single sort of like golden image for the partition, and everything is treated as a compute node. All right, so it's identical all the way through. We don't let the users like say, hey, we're going to spin up our own virtual machine with our own deployment. This is just a way of extending a traditional HPC structure within a cloud environment. But of course, that's not the only way to do it. And the University of Freiburg, with their NEMO system, do go the other way around. So whereas we've basically built this chimera, this multi-headed beast of sort of like bare metal partition with sort of like cloud partitions varying on the interconnect, they've actually said that we've got spare HPC compute nodes, and rather than having them sit idle, we're going to let their users submit their own images onto those compute nodes. So they either allow a cloud VM using OpenStack to be deployed directly on a compute node where they've got a static VM queue, or they allow the Horizon dashboard to submit to Moab, or they allow a Moab job to go onto a cluster node. So their system is a lot more complex. It's come the other way around. They've got more of a cyborg, we've got more of a chimera. So if I can just do a quick sketch, this is from the people at University of Freiburg. As you can see there, SSH or HTTPS onto either Horizon or as sort of like a simple login job, and then submitting either on a static VM nodes that they've put aside, or to basically go through the schedule, and that's a little extension that they have written themselves. So you can compare that. We've got a fairly normal system where people just submit to the partition cloud and it goes into virtual machines. They've adopted something that's more complex, but does have a different sort of flexibility. They have environmental flexibility, whereas we've adopted a policy of a management flexibility. And of course, with the existence of the Nectar Research Cloud, people who want their own particular workflow can actually sort of like, go spin up virtual machines on that instead in our environment, and that's not an option that they have. There's also the matter of cloud bursting. This is, for those of you who don't know that image, it's Willem Reich, somewhat crazed psychoanalyst from the 1930s to 50s, who believed that if he sort of like, had a machine that could sort of like, cause it to rain, so that's his rain producing machine. And cloud bursting is somewhat mythical, like Willem Reich's cloud burster, I'm afraid. There is a cloud bursting feature in Slurm, which is an extension of their power feature. So they've got a feature that basically says if a node doesn't sort of like, isn't being used for a while, it powers itself off, which is great. And extends that to say, well, when it powers itself back on, go to this cloud provider. When we first tested it, we discovered there was a bug where it meant that only about half the nodes turned themselves back on, which was not great, but that's since been fixed. And we've also had the issue of how do you do your local mounts. So if you want to do your cloud bursting, how are you going to mount your local home directories or your project directories or whatever? The only plausible solution to those issues in cloud bursting is basically to have a wrapper script and a copy of your local environment at your cloud provider in a more minimalist fashion. So yes, it is and can be done, but it is not as as grand as initial promises may or thoughts may have actually been. So yes, cloud bursting exists, but not as fully featured as we may have once upon a time helped, because, well, latency and copying of software stacks and mount points are actually a reality we actually have to concern ourselves about. Moving along, we take it a step further. Containers on a virtual machine on an HPC, or as I've given it the title, look, Mum, we've built a human pyramid. So containers, of course, are very useful if people have got that particular tool chain and they want to ensure extremely high levels of reproducibility because, well, you use that particular image. It is great in those single complex workflows. Docker, of course, uses as more designed for DevOps and microservices. We are using Singularity. We can, although it has got its own images, we can import and convert Docker images. Singularity does come with excellent support for MPI and GPUs, something what SC's shifter doesn't provide yet, but it is also another one to have a look at, particularly if you're using Cray systems. One of the things which is extremely important is that the way that Singularity does its security features compared to Docker. So Docker likes to run as root, and HPC sysadmins went universally went warning, 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 danger, Will Robinson. Some places ignored that, and lo and behold, be that on their head. Singularity has a method where the user has got the same level of permissions inside the container and outside the container. So if they actually want to make changes, they've got to make a copy. They've got to make a copy of their container on a local machine, make the changes, bring it back up. So there was a recent security exploit, Stack Clash, which did affect Docker binaries, Docker containers. Singularity and Shifter were protected from this because both of them have this method of ensuring that the user inside and outside the container have got the same permissions. And whereupon Disaster Girl reminds us once again that sometimes you need to ensure that you've actually got the, that you protect yourself from potential disaster. I mean, yeah, it should really come with a multi-guard, shouldn't it? It's like a software version thereof. But the main point of all this is not just to play around with the possibility of providing different architectures. The main point is that software problems, computational problems, do come in very different flavours, and different architectural environments are needed to actually ensure that we get throughput done. So whereas high performance computing, that pure hardware fashion, where we're trying to maximise the processing capacity is extremely important, sometimes we've got to think harder about matters of getting actual jobs done, because that's really what we're here for. Whether we're here as scientists and researchers, or as sysadmins, or as developers, or even as vendors, this entire industry is built around the idea of actually creating the tools so scientific and other researchers can get their computational tasks completed in the shortest possible time. And the reality is those computational tasks actually vary in what sort of architecture is most efficient. So rather than sort of concentrating really on a single physical performance, which is in fact actually abstract, we've actually got to think about more concrete performance, and that is the variety of actual computational tasks. And if we can provide those on a single platform, that becomes more transparent to the user. So there's my acknowledgements. Thanks to the HPC Advisory Council and Pawsey for organising this. Thanks to University of Melbourne and Bernard Mead for supporting my attendance, and to Dave Perry and Chris Samuel for their advice. Thank you very much.